Hello and welcome to the ninth session of this live interaction session. The course name is Advanced Thermodynamics and Kinetics. I am Umar Rashid, and every Friday I held a live interaction session with the students to solve some of the problems from the previous assignments and to give the brief introduction about the topics that are related to the questions that are asked in the assignments. So I briefly revise the fundamentals that are needed to answer the questions or to solve the assignments. So today is 31st. So I am starting this session. Okay, so as I told you before, like in our previous interaction, that all these recordings and these all the recordings and the study material will be available on NPTEL website. There is a link. So and also this video can be seen on the YouTube channel, and the links are shared on the Excel sheet that is shown. Uh, so today is the ninth session of this course, live interaction session. Okay, so without wasting time, let us start. Okay, now, nowadays we are mostly dealing with the spectroscopy and how we can predict a different spectra and what are the different kinds of the spectroscopy that we see in our day-to-day life. Okay, and uh, so we have I have told you about electronic spectroscopy in case of atoms, and how why are we seeing the why are we seeing the just we call it as a uh, uh, so this is the sorry. Okay, so this is NPTEL session 9. Okay, so the topic that we are nowadays doing is molecular spectroscopy. Okay, so I have told you about the atomic spectroscopy that gives the line spectra of atoms, and then I have showed you that from a particular atomic configuration how we can arrive at different atomic states, and from those atomic status how we can get atomic spectra. Okay, now we have a little more complex topic, that is the molecular spectroscopy. Now as I told you already that molecular spectras are complex. Why they are complex is because they are because of the different degrees of the freedom. We have electronic energy levels, right? Then we have vibrational energy levels, and then we have rotational energy levels, and translational. Now you have to see that the translational levels, they are not quantized, so as a result we don't see a spectra corresponding to a transition spectra, translational spectroscopy, but we have electronic, we have vibrational, and we have rotational. In the previous lectures I have briefly discussed you about the electronic spectra of molecules, how we can represent for example, as I showed you before, that if we have a diatomic molecule, how we can represent it as energy as a function of this is energy, and as a function of internuclear separation. Now this energy, it can be represented by a first we represent it as a parabolic approximation, right? So that is sort of like this. So this is a parabolic approximation. Then I have told you about what is it, 8's or secus 12 mu potential curve. This is also called as Leonard Jones potential. And then we have Morse, that most like that is very close to the real life situation, is the Morse potential. Okay, so sort of Morse potential is sort of similar to this, but it is little bit here. Okay, so this is the Morse potential. So we have explained. Now then what we have I have shown you is that in different states, what we'll have is we'll have in different electronic states, for example. Okay, so for example, if I make a this is energy and this is the reaction coordinate, then I have told you that if this is the ground state, this is the excited state. Okay, so in each of the ground states, so these are the electronic energy levels. Okay, I will write these represent electronic energy levels. Okay, then in each of the electronic energy levels we have, these are called as vibrational energy levels. Okay, in each of the vibrational levels we have rotational energy levels. Okay, so these are called as rotational energy levels. Okay, now this is the ground state, this is the excited state. So I will write this as an excited state, and I will write this as a ground state. Okay, now here also I will represent the curves. Okay, so we can have a transition in between these levels, like a light will come and the transition can happen from, for example, this state to this state, right? So what we have to give, we have to give energy h nu. Now that is called as an, this is called as an electronic transition. Okay, now since the electronic transition they are always vertical. Now I told you why they are vertical. This is called as a Franck-Condon principle. Now because of the Franck-Condon principle, the electronic energy levels are vertical. Now this is called as a Franck-Condon principle. So why they are vertical is because when an electron is excited, the nuclei are quite heavy, so the electronic excitations are very fast as compared to the nuclear relaxation. Okay, so now because of that the electronic transitions are also vertical. And also there is another thing, that you can have a transition from a higher electron density to that of to that of an electron density. If we see the vibrational states, Okay, for example, if we see, if I'll write here, okay, so I'll write like the ground level. So what will be it is, then I will write second level, then I will write third level, then I will write fourth level. Okay, so this is V is equivalent to 1, sorry, V is equivalent to 0, V is equal to 1, V is equivalent to 2, V is equivalent to 3. So if I make this as psi vibrational scale, so this is the scale of the wave function gives us the probability of finding an particle in that in a unit area, right? So if I, this is the wave function scale. Okay, for vibrational ground state, you see the maximum electron density is in the center. Now if you will go to wave function 2, okay, so it will be like this. Okay, then wave function 1, then we have wave function 2, it will be like this. Then wave function 3, it will be like this. So what happens is that as we go on increasing the vibrational wave number, the more electron density, or we can say that more the probability of finding a particle is more towards the end of the vibrational state. Okay, so for example, more is towards the end. For example, if we take a vibrational state, okay, this is a pendulum and it goes from here up to here, right? So here potential energy is V max. Here E kinetic is max. So the more probability is towards the maximum amplitudes. Okay, towards the ends of the same happens with that of an electron density in case of vibrational states. So as we go on increasing the vibrational status, the electron density is more and more towards the ends of that state. Okay, in say we can see in this area, because this is a vibrational state, right? So it can, an electron transition is more can more is happening from an higher electronic state to that of a, so if we make an electron density here, this is 1 2 3, so I have to make 4, so it will happen here to here, right? From maximum probability density to that of the maximum probability density in the state. Now this is called as a vibrational transition. Now in those vibrational transitions we have also the rotational transitions. Okay, first I'll discuss about this later. For now I will discuss a little bit about the rotational transitions and how the rotational spectroscopy is. Okay, for example, if we take a diatomic molecule. Okay, we take a diatomic molecule, so we have this, there is a separation between them, and this is moving in xy plane. So along the z it will have angular momentum, along the z axis. Okay, when it is moving along the xy plane, from the right hand thumb rule, it will have angular momentum along the z axis. Okay, now we know that what is the angular momentum along the z axis, as given from the classical principle, it will be I omega. Okay, so where I is moment of inertia and omega is rotational velocity. Okay, now so this is this. Now what is the energy of this state when the diatomic molecule is rotating in xy direction? The energy is, from the classically we can see that classically we can see that energy is 1 by 2 I omega square. Okay, so that will be given by, if we will write L square by 2 I. Okay, so this is classical energy for rigid rotor, right? So now it has an energy this. Now in order to make an Hamiltonian, what we have to do is we have to just convert this into, okay, then what we do is we solve the equation for this. Okay, and we will get something called as a quantum energy of this one dimensional or two dimensional rotor or a rigid rotor along whose momentum is along the z axis. So what we'll get is the energy will be equivalent to L square h cross square by 2I, and it is angular momentum is given by L h by 2 pi. Okay, so this is the energy of a quantum mechanical rigid rotor. Now if we make an energy level diagram of this, okay, we'll see that we'll make an energy level diagram. L is 0, so energy will be given by 0, right? So then we'll have a single state. Then L is equivalent to plus minus 1. Okay, energy will be same, h cross square by 2I, because 1 square is 1, then but there are two states, so it is degenerate. Okay, then similarly L is equivalent to plus minus 2, energy will be given by 4 h cross square by 2I, so you will have two more states. Similarly L is equivalent to plus minus 3, energy will be given by 9 h cross square by 2I. These are all. So what we have is, we have, if we write here degeneracy, you have one degeneracy, you have two states, you have three states, you have four states. So this is for a rotor which has a whose angular momentum is along the z axis. Now if we have a three-dimensional rotor, for example an electron moving over a C60, okay, or we have a okay, so we have a diatomic molecule that is moving in all the directions. Then it will have it will have Lz, right? Then it will have Lx and it will have Ly. So it has angular momentum along the three directions, and also it will have total energy. Now okay, so once we solve it, we have to use in the quantum mechanical equation both for Lx, Ly and the Lz and the total energy. Now what we get in terms of an energy is, we can write it as a jj plus jj minus 1 h cross square by 2I. Okay, so this is the energy, and L plus 1 h by 2 pi is the angular momentum, the magnitude of total angular momentum. Okay, however along Lz, okay, so now what I have written here is, for a rigid rotor which is moving in 3 dimension, we will have a total energy j plus 1 h square by 2I. Okay, and the magnitude of the total angular momentum will be l plus 1 h by 2 pi. Okay, and the angular momentum along the z axis will be ml h by 2 pi. Now this ml, okay, we have an ml. Now ml, the value of an ml goes from minus l, sorry, if I will write ml, then I have to write here l or j. You can write mj, it's okay. So value of mj changes from minus j to plus j, and its value is okay. So the degeneracy of these levels are 2j plus 1. Okay, so what I have shown you here is uh, I have shown you a one-dimensional, two-dimensional plane single rotor which is moving in xy direction, xy plane, and it is and then I have showed you a three-dimensional rotation. In three-dimensional rotation, we'll have angular momentum along three axes: Lx, Ly, and Lz. And if we solve the quantum mechanical equations, we will get energy, that is jj plus 1 h cross by 2I, and we will have a magnitude of total angular momentum under root of ll plus 1 h by 2 pi, and the angular momentum along the z axis will be m h by 2 pi. Okay, now we know now this ml is going from minus j to plus j, therefore the degeneracy of the levels will be 2j plus 1. So as we go on increasing the j, the degeneracy will increase. Now if we put, for example, we'll see how the energy levels are looking. Now if we put j is equal to 0, how much will be the energy equivalent to 0. Okay, and degeneracy will be 1, 2j plus 1, that means 2 degeneracy will be 1. Okay, so we'll write 2j plus 1 here. Okay, so I'll make an energy level here. Okay, so degeneracy will be 1 here. Now what will go is, we'll go j is equivalent to 1. Okay, energy will be given by 1, so sorry, here it is plus. Okay, so jj plus 1, so it will be 1, j plus 1 is 2, so 2 h square by 2I. Also what I will write is here E is equivalent to j plus 1, and then in b, so b is called as rotational constant, and b value is h cross square by 2I. Okay, so we got bjj plus 1. Now how much will be the energy in terms of b? It will be 2b. Okay, then degeneracy will be 2 plus 1, it will be 3, 2j plus 1, 2 multiplied by 1 plus 1. Now then we have j is equivalent to 2, e will be, so this will be 2, 2 2s are 2 plus 1 is 3, 3 2s are 6. Degeneracy will be 7. To 12b, then so energy will be this, degeneracy will be sorry, here it will be 5, and this will be 5, this will be 7. Okay, so we can make 3 energy states, then we can make 5 2 3 4 5, 1 2 3 4 5 6 7, okay, which have the same energy state. Similarly, we can write J is equal to 4, the energy will be 4 5 4 20 B, and the degeneracy will be 9. Okay, so now we have these energy states. Okay, now we want to see a transition that is happening. Okay, so first transition I will see from first state to this state. Okay, if we have a transition from this state to this state, okay, it will give me an energy that will correspond to a single line. Okay, and it is difference will be 2b. So when a transition will come from j is equal to 1 to j is equal to 0, its energy state will be 2b. Okay, the energy of that will be 2b. Now if we want a transition now from here to here, what is the distance, the energy separation? It is 4b. 6 minus 2 is 4b, so we'll see another peak at 4b. Okay, then we will see if we want to see a transition from here to here, what is the difference? 6b. We'll see a transition at 6b. So if this is our intensity and this is our energy state, okay, then from here to here it will be at 8b. So we'll see another transition at 8b. Okay, so this is rotational, pure rotational spectrum. This is a pure rotational spectra of a rigid rotor in 3 dimensions. So what we are seeing is that we will see an equally separated lines. Each of the separation is 2b. This is what we expect from a rotational spectra of a diatomic molecule. Okay, but the problem here is the rotational of a diatomic molecule is this is a rigid rotor. Okay, we have not taken into consideration the centrifugal distortion. Okay, now once we introduce the centrifugal distortion, what will happen is that centrifugal distortion occurs at very high J values. Oh, okay, so high J values it will happen. So what happens is centrifugal force is applied to a molecule once it rotates very high. Now because of that, since B is given by h cut square divided by 2I, which is given by h cut square divided by 2 mu r square. Okay, where mu is the reduced mass and r is separation. Okay, at higher J, once we are rotating our diatomic molecule very high, okay, with high angular velocity, what will happen is the centrifugal force will come into the picture. Because of that, R increases. So because B is inversely proportional to R, okay, that means B decreases. Okay, so what you will see is that for a centrifugal force, if we are seeing equally distant lines for an ideal case, right, These are equidistant lines. So this is at 2b, 4b, 6b, 8b, 10b, and the separation is 2b. But once there is a centrifugal distortion, this peak will, this will come at here, this will little bit come closer, this will little bit come more closer, this will little bit come more closer, it will become more closer. Okay, so these status are with distortion. So B decreases as J increases. Okay, so this is how we will get the real spectrum. You will have higher on higher J values, you will have the B lines that are closer than should be present at the 2b. Okay, so if we want to derive, if we want to collect the information from the rotational spectra, like we can have the reduced mass from the rotational spectra, or we can have the internuclear separation from the rotational spectra, we have to take the first two lines of the rotational spectra, and then from that we'll take the value of the B. This value of the B is, as I have told you, it is given by h cross square divided by 2 mu r square. We can calculate the value of the interatomic distance. Okay, so this is briefly the rotational spectroscopy of a diatomic molecule. Now, in majority of the molecules, the molecules, since the rotational states are closely spaced, the molecules absorb the rotational spectra in the rotational energy levels in microwave region. Okay, so we have to remember that this happens in the microwave region. Now we'll go to the vibrational transitions. Now we'll go vibrational spectroscopy. Now we'll go to the vibrational spectroscopy. In vibrational spectroscopy, as I told you, the vibrational states are involved. Okay, we'll see transitions in the vibrational states. But as I will tell you that once you apply a frequency in IR region, what will happen is that we will see both vibrational plus rotational transitions. Okay, so we'll see both vibration as well as rotation. That is the reason the infrared spectroscopy is called as vibrational rotational spectroscopy, because the energy status, the energy gap between the rotational states is less as compared to vibrational state. So if you give higher energy, like equivalent that of the vibrational status difference, we will see a transition in both rotational as well as the vibrational states. Okay, now for vibrational spectroscopy, what we'll do is we'll just take two diatomic molecule, and we'll consider that the bond between them is connected by a superring. Okay, suppose it has a mass of m, it has a mass of n, and it's the superring. This is the superring, and superring constant is this. Now if it is vibrated towards the x direction, okay, x, and we fix this at a 0, now what will happen is that it will apply a backward force that will be given by F is equal to minus k of x. Okay, where k is called as a superring constant. This superring constant will tell us more about bond and everything. Okay, now the energy is given by, the classical energy is given by 1 by 2 k x square. Okay, so this is classical energy of S supreme. So, okay, so in quantum mechanics, we solve this equation. We have something called as a Hermite polynomial. So the equation comes in that. So we'll design a Hamiltonian for the vibrational state from its classical analog, and from that then we can calculate energy. The energy comes out to be V plus 1 by 2 h nu. Okay, so this is energy of a quantum oscillator. Now it is harmonic oscillator. A harmonic now there is a difference. What is a harmonic oscillator? In case of a harmonic oscillator, the backward force is always directly proportional to x. Okay, so that is only possible when of the amplitude of vibration is small. Okay, so if we have a okay, so this is the so we have a for example a pendulum, or and then it is moving along this direction, it is moving along this direction, or we can have a spring. Okay, so it can have x and it can have x. So this is a harmonic oscillator. Now we have seen the energy of an harmonic oscillator is given by V plus 1 by 2 h nu, where nu is fundamental frequency of vibrator. Okay, so nu is the fundamental frequency of the vibrator. Okay, now I will tell you why is it called as a fundamental. If we see now, we can change from 0 1 2 like this. So this is called as vibrational quantum number. So V is vibrational quantum number. Okay, vibrational quantum number. Now we'll see the energy E for V is equivalent to 0. How much it will be? 1 by 2 h nu. Cool. Now this V is 1 by 2 h nu. So even if a vibrator is having is at 0 vibrational quantum state, it will always have some energy. This energy is called as 0 point energy. It is the energy that is retained by the matter, by molecules, even at 0 Kelvin. Okay, 0. So even if the total vibrational quantum number is 0, vibrational ground state a molecule is, it will still have a particular type of energy that is called as a 0 point, and that 0 point energy comes because of the vibrations. Okay, this mu is also given, this mu we can represent as 1 by 2 by under root k by mu. Okay, so this is the fundamental frequency you can get from any band. So if also we can have the rotational velocity is equivalent to 2 pi mu is equivalent to under root k by mu. Okay, so if uh, k is high, the mu is high, right? That means k is directly proportional to the mu. K is directly proportional to the fundamental frequency. Okay, so higher the bond strength, so bond strength is for example, if we'll take k for a single bond, it's a weaker bond, right? It will be less as compared to k for a double bond, as compared to k for a triple bond. Now we know that k is for less than single bond, then for now this k is directly proportional to mu. So if we take the fundamental frequency for a single bond, it will be higher as compared to that of a double bond, as compared to that of a triple bond. So from this we can actually separate different types of the bonds in a system, whereas mu is called as a reduced mass. So mu is given by m1 m2 divided by m1 plus m2, and this is called as reduced mass. Okay, now we'll make the different energy states. We have a vibrational energy equivalent to v plus 1 by 2 h nu. Okay, so when v is equivalent to 0, what will be the state? The energy is given by 1 by 2 h nu, then v is equivalent to 1. Okay, the energy will be given by 3 by 2 h nu. Actually, 1 minute. So here, as sorry, I made a mistake here. The L can only have positive values. Okay, it can be either a positive 3 positive integer values, but ml can have both positive as well as negative values. Okay, yeah. So here also the degeneracy is 1, then the degeneracy is 2, then the degeneracy for others is 2 2. So it has 1 2 2 2 degeneracy. Okay, but once we go to the uh, 3D rotor, we can have a different degeneracy. That this degeneracy will depend upon what is it is mj value. Okay, okay, so now we have a reduced mass, we have energy equivalent to this. Now we have 3 by 2. Okay, now if we take another vibrational state, that is v is equivalent to 2, the energy will be 3 by 2 h nu. Similarly, v is equivalent to 3, the energy will be 5 by 2 h nu. 1 2 3 4. Now if we take now rotational status, as I told you, they have the degeneracy, or degeneracy is equal to 2j plus 1, but vibrational status doesn't have degeneracy. Okay, so they have single degeneracy. Okay, now if we see the transition, this is at 1 by 2 h nu. What is the transition that is coming from here to here? It will be equivalent to h nu. What is the transition coming from here to here? It will be h nu. What is the transition it's coming from it? It will be h nu. So the vibrational spectra for a particular bond, it will be a single line. Okay, so I will write is a vibrational spectra. So it will be a single line. Now because of broadening, it will have some, because of the transitions in rotational and these status, it will have some broadening, so you will get a single peak that is corresponding to that of the vibrational spectroscopy. Okay, now in vibrational spectroscopy, we represent the vibrational spectroscopy in terms of or infrared in terms of a transmission. So the transmission will just be the opposite of this. Okay, so if this is absorbance, if we'll cover that with the transmission, so the transmission will be like this, then it will be this. Okay, mission, this is 0%, this is 100% transmission, this is 0% transmission. Okay, okay, so this is the vibrational spectroscopy, and this is written in terms of wave number. Okay, wave number is just an inverse of what uh, wavelength. Okay, so for example, if we write E is equivalent to h nu, okay, this is in terms of nu, then E is equivalent to h c by lambda, right? Then E can be written in terms of wave number as, okay, here V is frequency, lambda is wavelength, and this is wave number. So vibrational spectroscopy is mostly, infrared spectroscopy is mostly shown in terms of transmission as a function of the wave number. Done. Just like the carbon carbon triple bond absorbs at 3300 wave number. Okay, so you will get a single line that corresponds to fundamental frequency, that is the fundamental transition that is happening from n is equal to 2 to n is equal to 1, or and also from the other transitions from n is equal to 3 to n is equal to 1. Here n is v, so from v is equal to 1 to v is equal to 0 you will get a transition, and that transition coincides with that of all other transitions from single level transitions from 2 to 1 and from 3 to 1. So but in case of a rotational transition, that is not the case. The fundamental transition comes at 2b, then another comes at 4b, then another comes at 8b. But since the fundamental transition is very also since there is a degeneracy, okay, in the rotational energy status, and the energy of the rotational levels is comparable to that of the thermal energy that's available at the room temperature. So the most intense peak we have to see considering the degeneracy as well as the Boltzmann distribution, where so the maximum transition will be which where there are maximum number of the status from the ground state to that of an excited state, if we talk about the absorption spectroscopy. Okay, so I have so this is called as a vibrational transition. Now once we apply a frequency, for example, now this is a vibrational line. Okay, okay, so as I told you that each vibrational state has a different rotational states. Okay, so then once we give a particular frequency, what will happen is that there can be a concurrent rotational states, rotational transitions as well. Okay, now those transitions are a little weaker as compared to the main transition. Okay, and that is called as a vibrational rotational spectroscopy. Okay, so this will call as, okay, now whenever there is a vibrational transition. Okay, like for example vibrational, whenever there is an absorption, for example from one vibrational state to the higher vibrational states. Okay, what will happen is that that absorption can happen from, if I will write here, I'll just make two vibrational states. Okay, and then there are various rotational states. Okay, so these are various rotational states and these are vibrational state. Now I'll write this v is equivalent to 0, this is v is equivalent to 1. Okay, now this state is called as, I'll write j is equivalent to 0, j is equal to 1, j is equivalent to 2. Similarly j is 0, 1 and 2, j, j. Okay, now if a transition happens from one vibration state to another vibration state, okay, this thing is whole a single vibrational state. Okay, probably I should have written that way. So this is v is equivalent to 0, this is v is equivalent to 1. Now if a transition happens, for example from j is equivalent to 0 to that of j is equivalent to 0 of this one state, so this transition is from j 0 to 0 transition. Okay, so this transition is happening from j equal to 0 to 0 transition. So for that we'll get a spectral line that is actually here. Okay, now if a transition happens from j is equal to 0 to j is equivalent to higher state, for example j is equivalent to 1, so what we'll have is we'll see another line, but energy intensity will be less, but the energy is higher. The difference between the energy will be the difference between j is equivalent to 1 to that of a j is equal to 2 state. Okay, the difference in these energy, that means the energy difference between sorry, this is here, from the difference between j is equal to 0 to j is equal to 1. Similarly, and another transition can happen from this to this. Okay, so you will see another small line that is occurring here at higher energy. Okay, now uh, it will be given by the difference in the energy that is present in the excited state rotation energy levels. However, a transition can also happen from j is equivalent to 1 to j is equivalent to 0, like this. So you should see another transition that is lower frequency, that is this. Another transition can happen from j is equivalent to 3 to j is equivalent to 1. Okay, so you will see another line that is here. So what will in vibrational rotational spectroscopy is we will have two types of the lines. Either we will have we'll have higher than the fundamental frequency, or we will have lower than the fundamental frequency. Okay, of the fundamental frequency of the, Okay, as a result what they do is they form a band. Okay, so vibrational rotational spectroscopy, instead of getting uh, what is instead of getting single lines, what you will get, you will get a band of lines. Okay, that uh, uh, band of lines, they or we call it as a branch of lines. Okay, so you will have uh, so different branch of the lines we will get. Okay, one branch is lower than the j is equal to 0 to j is equal to j excited zero transition. Another branch is j is equal to higher transition, but there is another there are more transitions that are possible in this, is when the transitions happen from 1 0 to 0, then 1 to 1, then 2 to 2. Now all of these will have same, so they those things will come in this will also come in decision. For example, you will have another transition from this, we have considered from 0 to 0, but you can have transition from 1 to 1 also, you can have transition from 3 to 3 also, right? Okay, so that will also come around the similar frequency. So this, no, this area of the side is called as a P branch. The middle is called as a Q branch, and the end is called as R branch. Okay, so we will have three branches. One is the middle branch, that is Q branch. Q branch is where there is no rotational transition. Okay, there is only vibrational transition. Then we will have P branch, where there is a decrease in the rotational. For example, from ground state vibrational v is equal to 0 to v is equal to 1 to v is equal to 0 in the x state. So there is decrease in the rotational number. Rotational transition is minus 1. Whereas in R branch, what will happen is there is a transition in from ground state vibration to excited state vibration, but there is an delta j is equal to plus 1. Okay, so in pre branch, delta j is minus 1, here delta j is 0, here delta j is plus 1. Okay, so this is how rotational vibrational state transitions appear. Okay, so you have to see that for a uh, for a rotational vibrational state, you will have both vibrational states as well as vibrational transitions as well as the rotational transitions. Okay, the now if you see for transitions that are like delta v is equivalent to plus minus 1. Okay, that means we are seeing a vibrational transitions. Okay, the selection rule is like a set of rules that tell us which of the vibrations or which of the transitions are allowed and which of the transitions are forbidden transitions. Allowed transitions are those transitions whose intensity is very strong. Okay, and the forbidden transitions, the intensity is very weak. For selection rules for delta g plus 1 is that delta v should be plus minus 1, and for delta j is equivalent to 0. For example, this q branch, right? That is what I have shown here. It is actually a forbidden transition. Now this I am talking about a heterodiatomic molecule. Okay, so as a result you will not see the Q branch in case of heterodiatomic molecule. This is first selection rule. The second selection rule, if we'll say, is that the delta J is either plus 1 or it is either minus 1. If it is plus 1, then what we'll have is our the line will come above Q branch, and if it is minus 1, the line will come uh, below Q branch. So that comprises of P branch and R branch. Okay, but for heterodiatomic molecules, if we see that these transitions are all, not required. Like these forbidden rules are these selection rules, they are relaxed. So as a result you can have both P, Q as well as R branch. Okay, and for Raman spectroscopy you have to see where we see for Raman spectroscopy delta J should be plus minus 2. Okay, 0 or plus minus 2 transitions are allowed. Okay, so we call that as a if it is O branch, if the transition is happening delta J is minus 2, and we call that as S branch if delta J is plus 2. Okay, so we'll have O branch, then in the middle we'll have Q branch, and then we'll have S branch. This is in Raman spectroscopy. Okay, this is in Raman spectroscopy. Why? Because here delta J is plus minus 2. Now these selection rules are for heterodiatomic molecules. Okay, so different molecules will give different transitions as allowed and forbidden depending upon if the dipole moment and if the dipole moment or if the polarization is changing. So a transition will be an allowed transition only. I think before that I'll give brief discussion about the selection rules. Okay, so we have already explained this what is for diatomic molecules. So here I am showing you the fundamental frequency for a number of molecules for diatomic molecules. So you can see for HF, for HR, for HBr, and as we go on increasing the as we go on increasing the value of an I, as I told you that the fundamental frequency is directly proportional to k by mu. As we go on increasing the mu, that means the reduced mass, the fundamental frequency should decrease. So that is actually happening here. HF is lighter, so fundamental frequency is high, then lower, then lower, then lower. Okay, similarly we have carbon monoxide, and then we have the force constant. So if we see HBr, this and this, the force constant is because they have a single bond in between them, so the force constant is less. But as we go on increasing the for example it has a C double bond O, okay, the force constant is high. Okay, now we have something called as a selection rule. So what is selection rule? Okay, Selection rule is something that tells us, that guides us to read a particular to say where a particular transition is allowed or not. So as I have written here, the selection rule or transition rule, it's actually a constraint to the transitions that are happening. So it tells us whether the particular transition is allowed or forbidden. They are derived because of by considering the electromagnetic transition of the molecules and the light that we are giving. Okay, so different techniques have different selection rules. For example, for rotational selection rule, it is delta J is equal to plus minus 1, but if we go towards the Raman spectroscopy, the delta J should be plus minus 2. Okay, so for different techniques, the selection rules is different. Okay, so these rotation selection rules, they are derived by calculating the transition dipole moment integral. Now that transition is allowed where the transition dipole moment is equivalent to 0. If the transition now you see this okay. So yeah, so as I told you, that selection rules are derived by an integral called as a transition dipole moment. Okay, so the transition dipole moment tells us like how much the dipole moment will change, integration of the dipole moment when a particular transition will happen. Okay, so yeah, so this transition dipole moment is actually shown here. Here it is integration of psi 1 state, psi 2 state, and mu and d tau, where psi 1 dash is the ground state. This is the excited state, psi 2 is the excited state, and mu is the transition. It is concerned with the transition that we are trying to do. Okay, this determines actually the transition probability. Okay, so it is where this as I told you, that psi 1 and psi 2 are two different eigenstates, and this mu is the electrical dipole moment operator. Okay, so the electrical dipole moment operator can have a like depending upon what we are trying to do, it will have a different state. Okay, so by deriving this by calculating this transition dipole moment, we can see that if a transition is allowed or the transition is not allowed. Okay, now different as I told you, different spectroscopy have different this mu will be different for different spectroscopic transitions. Okay, so on the basis of that, we can determine what is this transition dipole moment integral. The easiest way from the transition dipole moment is derived by from the symmetry rules. Okay, it is easily derived from the symmetry rules or symmetry selection rules. Okay, so from the symmetry rules, we assign the symmetry corresponding to mu 1, mu then phi 2 and d phi, and from that we can determine what is the transition dipole moment integral, and from that we'll see if a particular transition is allowed transition or a particular transition is a forbidden transition. Now, a transition is possible when this transition dipole moment integral is not equivalent to 0, and if the transition dipole moment is equivalent to 0, then the transition is not possible. Okay, so if it is the transition, this is allowed if it is equivalent to 1. It is not allowed, the particular transition is not allowed when it is equivalent to 0. Okay, so this is how the selection rules are derived. As I told you that the selection rules can tell us about uh, whether a transition is allowed or a transition is not allowed. Okay, so now as I have told you about, or I have told you about different transition frequencies, sorry, different vibrational techniques or different spectroscopic techniques, and what are the different rules. So then we'll see the questions, okay, and we'll try to answer them. Okay, so what is the first question is, during a vibranic transition, so you have a both vibrational as well as an electronic transition, the selection rule for vibrational transition is, so what we are seeing is that when we have a transition of both vibrational as well as electronic energy levels. Okay, so both vibrational as well as electronic energy levels, what is the selection rule? So for that delta v is 0, so either neither it is delta v is equal to 0, neither plus minus 1, neither plus minus 2, so it is none of the above for vibranic transitions. Okay, now we have question number second. During the vibranic transition to all the vibration states of an electronic energy levels are occupied. When there is a vibranic transition, that means when there is a both vibrational as well as the electronic transition to all vibration states of electronic energy levels are equally probable. See, probably I'll explain a little bit, as I have shown you before, these two states, right? So this is a vibration transition. The transition goes from here up to here. Now as I told you that the selection rules are always, the selection rule is Frank-Conan principle. So Frank-Conan principle that the vibration transitions are always linear, now always vertical. Now it can happen here, it can happen here, it can happen here, so there is no definite vibrational transition rule for that. Okay, so as a result delta v is equal to none of the above is the correct answer. The second is that if we have a vibrational transition as well as electronic transition, what will happen? First is, during vibranic transition, transitions to all vibrational states of an electronic levels are equally probable. During the vibranic transition, the nuclei have same position before and after the transition C. This is the correct statement as per the Frank-Conan principle. The transitions are vertical, that means the nuclei doesn't change. During the vibranic transition, the nuclei have same velocity before and after the transition. Okay, so the correct answer is 2 and 3. Okay, so these are direct consequences of the Frank-Conan principle. Okay, which of the following accounts for an increase in temperature of a stratosphere? Okay, so I'll tell you briefly about the stratosphere. Okay, so stratosphere is actually an atmospheric sphere. That is from, like you can say, it is from 25 kilometers from Earth. Okay, so it is in the upper part of troposphere. So troposphere is a sphere that is touching the ground. Okay, so we have, for example, we have the earth's surface, right? Then from the earth's surface we have a troposphere. Okay, then we have mesosphere. Okay, so the stratosphere is actually in between mesosphere and troposphere. Okay, so what is more important in the stratosphere is that the stratosphere, it consists of UV radiation, it consists of ozone layer. That ozone protects the earth's environment from the harmful UV radiations. Okay, so what how it does is that there is the plenty amount of ozone is the allotropic form of oxygen, this. Okay, ozone, O3. So this ozone protects from the harmful UV radiations. So what happens is that if we have a for example, here what happens is there is repeated making and breaking of the ozone, O3, from the oxygen. So we have O2. Okay, then once you put UVC radiations that are around 240 nanometer. Okay, what happens is they it produces radicals. Okay, now these radicals, they combine with oxygen to form O3. Okay, 3 times O3. So this is called as an ozone. Now ozone, what ozone undergoes photolysis again to produce O plus O3. Okay, and this O combines with O2 to form O3 and releasing plus heat. Okay, now this heat is released because of combination of O plus O2. This process happens in stratosphere. Because of the repeated process, what we are seeing is that we are seeing a very high temperature in the stratosphere. Okay, this occurs because of absorption of uh, UV radiations by the ozone or oxygen, by repeated formation breaking of oxygen. Now we have to see what is the following accounts for increase in temperature of air: absorption of infrared radiation, absorption of air, thermalization of absorbed radiation. So the third is the answer. Okay, as I have told you what is actually happening. Okay, the UV radiations come, they get absorbed, they break. As a result, because of that breaking, because of that breaking, we release heat. That heat is responsible for increase in temperature of the stratosphere. Now this is a very important process, and recently there was an issue that ozone layer depletion. It is because that ozone layer depletion occurs because of either chlorofluorocarbons or ozone depleting substances, okay, which release nascent chlorine, nascent okay, halides. So what happens is that those halides, they react with the ozone, and they convert it into oxygen back. It leads a chain reaction. As a result, we'll have a hole in the ozone, and the UV radiations can directly pass. Now that was a concern some years. Nowadays it's not that much of a concern uh, because of the healing of the ozone layer. Okay, so we'll go to the fourth question. For a hypothetical reaction, now we have a reaction. Okay, this is question number 4. Let me take 1 minute break. Okay, so we have an hypothetical reaction, that is A2 gives to 2A, reaction constant is O0, B2 gives to 2B, then we have a chain branching, that means A combines with B2 to produce more B, and B combines with A2 to produce more A. Okay, then we have a chain propagation, that means AB combines with A2 to produce A to B plus A, and then chain termination, A combined with wall to produce this. Okay, so we have an hypothetical reaction in which A and B, they undergo this sort of a chain reaction. What happens is there is an initiation, that is formation of a radical, then there is chain branching, like different radicals get formed, then those radicals they initiate chain reaction. Okay, and at some point, like the walls of a vessel or some uh, external agent that is added to stop the chain reaction. Okay, so this is a hypothetical reaction, and here the question is, how is the maximum product, that is why is the maximum product is formed. So value of the G is given as 2.5 into 10 to the power minus 7 F omega T F and G. So we have to determine from where the maximum product is formed. Okay, so what we'll do is we'll go back here and we'll see we have question number 3 on the assignment. Now what is written is that G is given by K4 plus K5, then B2 into M. Okay, the value is given as 2.5 into 10 to the power minus 7 unit. Also F is given as 2 K2 B2. So now if now we'll look at these. Now you see, if there is this is the F value. F is mean F tells us about this K2, that means chain branching, more and more branches are being formed. Okay, whereas G tells us about chain termination. Okay, now from that we will see that if G is greater than F, then what will happen is then termination will dominate. Right, because this depends upon the rate constant of the termination. But if F is greater than G, then what will happen is branching will dominate. Okay, now as is written from this 2, that F is greater than G. So this is 5.87 into 10 to the power minus 7. So what will happen is major product will be formed due to branching, right? So that is the answer. So the answer is B. B is the answer. Now here, as I have showed you before, which of the below reaction is responsible for shielding of earth from harmful UV radiations. Okay, so we have to see which is responsible for shielding of UV radiations from Earth's atmosphere? So this is question number 5. Okay, as I told you that once the H nu comes, it strikes ozone, it gets broken down into O2 and O. So as a result, it is absorbed there and it does not reach the Earth's surface. So this reaction is responsible for shielding of Earth. So this answer is C. Okay. Now question D. Question number 6. According to Kasha's rule, which among the following is corrected? Photo emission. Now this is a simple question. Okay, so here this is question number 6. According to the Kasha's rule, which among the following is corrected? The photo emission is appreciable from the second excited state. So the third, C, is the answer. Okay, for question number 6. Wait. Okay. So D is the answer. Sorry. So D is the answer because emission is always appreciable from the lowest excited state because it is very near to the closest state. So this is the Kasha's rule. So that is the D is the answer. Question number 6. Now question number 7. Time for the phosphorescence is. So as I showed you before that there is fluorescence and there is phosphorescence. Okay, the fluorescence is very fast process. Once it absorbs, the fluorescence happens back. So de-excitation happens and the fluorescence happens. Okay, but the phosphorescence is a delayed process. It happens. It is actually a forbidden transition. So it can happen even for hours after the absorption has taken place. So it's a low process. The time for the phosphorescence is order of microseconds. D is the answer. Now we have question number 8. What is the energy of a vibrational level in terms of angular frequency? Units of angular frequency is per second. We have to write what is the energy of a vibrational. V is equal to 4. Question number 8. Okay, V, as I already told you, E is equivalent to V plus 1 by 2 H. We'll write here omega. Okay, H hat omega. Because H hat is equivalent to H by 2 pi and omega is equivalent to 2 pi nu. Okay, so that we know. Now we have given in is 4 and value of the H hat is 0.55 into 10 to the power minus 34 joule second. So E is 4 plus 1 by 2 multiplied by 1.055 into 10 to the power minus 34 joule second omega per second. Units of the omega is per second. So the second and second will cancel, right? This will become equivalent to 9 by 2 into 10 to the power minus 34 omega joule. That is 9.495 divided by 2 multiplied by 10 to the power minus 34 omega joule. 747 into 10 to the power minus 34 omega joule. Okay, so the answer is 4.75 into 10 to the power minus 34 joule. simple. So what we had to do is we had to do nothing. I already showed you the equation for energy of a quantum vibrator. Now from that, what we have to do is we have to use v is equal 1 by 2 h nu, use the value of the h hat, use the value of the v, and from that we can calculate this. So from this we'll see that the answer is second one, B. Okay, so we have to determine the 0 point energy of an harmonic oscillator. I already told you what is the 0 point energy, that is equal to 1 by 2 h nu. Okay, why is it called as a 0 point energy is because it is still available for a molecule when the molecule is at absolute zero. Okay, even when B is equivalent to 0, this is the 0 point energy. Okay, which has mass of this and the force constant of this. Now we have been given mass and we have been given uh, force constant. We have to calculate the 0 point energy. It is very simple. Okay, so let us go to question 9. Okay, so we have to calculate the zero-point energy of harmonic oscillator. We know that energy of a harmonic oscillator is V plus 1 by 2 h cut this, right? Now for zero-point energy, V should be 0, so V is equal to 0 will be given by 1 by 2 h cut omega, that is equal to 1 by 2 h cut omega. So this is our value. Now this h cut value is given by 1.055 into 10 to the power minus 34 joule second. Okay, similarly we can calculate angular frequency, that is omega is given by under root k by m, right? So where k is given by force constant and m is mass of oscillator, so omega will be given by 255 Newton per meter by okay, so this is given. Now what we will do is we will calculate how I have done it is we know that 1 Newton is equivalent to kg meter per second square. It is force. Newton is a unit of the force. So we calculate the value of this. It will be 55.68 into 10 to the power 26 per second square under root, right? So if we take the under root, we'll write 7.46 into 10 to the power 13 per second. Now we have E is equal to 1 by 2 0-point energy, right? We'll write corresponds to 0. that is given by 1 by 2 multiplied by value of h cut, that is 1.55 per joule second. Okay, then multiplied by omega per second. So we can put v is equal to 0, e is equal to 3 point. This is our answer. Okay, so if we see back 3.94, this A is our answer. So we have determined the 0 point energy from that of the but if we have the values, because we can determine what is the 0 point energy from the equation. Okay, now the last question we have is, which of the following is not correct about fluorescence emission? Okay, I told you what is the fluorescence. So fluorescence emission is Stokes shifted with respect to absorption spectrum. Fluorescence emission is faster than phosphorescence. Fluorescence emission is faster than vibrational relaxation. Fluorescence emission is maximum for lowest than the vibrational relaxation. Now we have to see that which is not correct. Fluorescence emission is Stokes shifted with respect to absorption spectrum. Now why we have to see what is Stokes and anti-Stokes shift is. Stokes shift is once the absorption that we give is, once we get the light back, it is having lesser energy as compared to that of the absorption that we have given, that is Stokes shift. However, if we give some energy and the light that we get back has higher energy as compared to that of the absorbed light, that is called as an anti-Stokes shift. Okay, so we have an anti-Stokes line, we have a Stokes shift. Okay, and then we have the absorption. Now once the fluorescence occurs from a ground state to that of an once the absorption first occurs, so then first there is an vibrational relaxation. Okay, now fluorescence is not faster than the vibrational relaxation. First the vibrational relaxation occurs to some ground state vibrational states, then the fluorescence occurs. So first thing is, fluorescence emission is Stokes shift with respect to absorption spectrum. What happens is that once we give the absorption, now the light that is given, that is absorbed by the substance, will be higher energetic as compared to that of the light that we get, because there is a vibration relaxation. Okay, so the first one is correct. Second one is fluorescence emission is faster than phosphorescence. Yes, fluorescence emission is very fast as compared to the phosphorescence occurs when the absorption, when the relaxation, when uh, the light is given from a nearby triplet state to that of the ground state. Okay, so since triplet to singlet state is vibrationally forbidden transition, so what we have is we'll always see uh, fluorescence is very faster as compared to phosphorescence. Okay, then third is fluorescence emission is faster than vibrational relaxation. Now this statement is wrong. Third statement is maximum for the lowest. Yes, so fluorescence emission is maximum from the low, as I told you that fluorescence, once the absorption occurs, the molecule relaxes to the ground excited vibration vibrational ground state of the excited state. Okay, now from that the fluorescence occurs to the ground state, so obviously the fluorescence will be maximum from the uh, lowest vibrational state of the excited electronic state. Okay, so the correct answer is the C. So C is actually not true for the fluorescence, because fluorescence is much faster as compared to the is not faster as compared to that of a vibrational relaxation. Okay, so this completes our today's talk. So we'll take another assignment. Okay, so I will briefly uh, show you what briefly sort of give a tour of what we have done. So today we were working with the molecular spectroscopy. Okay, so we have I have told you how why the atomic spectral line spectra occurs because of the quantization, and different electronic configurations have different states. Because of that status we will have different spectral lines. Okay, then molecular spectroscopy is complex, as from the electronics we can have electronic, vibrational, rotational spectra which are quantized levels. Now electronic levels, electronic transition we see in the UV visible spectroscopy. Okay, so for a particular molecule, it has whole molecule has what we call them as a molecular orbital. So electronic transition occurs from molecular orbital, from one molecular orbital to one molecular orbital. So once we see the electronic transition, okay, now this is important, we see an electronic transition for a whole molecule. So there will be a one broad peak for a whole molecule. But once you see the vibrational transition, vibration you will see for each individual bond of a molecule. So for each individual bond it will vibrate. Okay, for example we have methane. If methane will absorb UV visible, we will see peak. Okay, but if you see vibrational transition, now you can also see like multiple peaks sometimes from n to pi transitions or pi to pi transitions. Okay, so okay, so that depends upon what we are dealing with, but they comprise of the whole molecule. Okay, but in case of a vibrational state, we will see the vibrational peak corresponding to each of the bond. Oh, and then we have a rotational state. We'll see the rotational with each of the rotational state of the molecule. Okay, this also corresponds to the molecule. Okay, then we have an electronic spectra that, for example, diatomic molecule, it can be sort of approximated by a parabolic, then by a Leonard-Jones potential, and then more accurately by a Morse potential. Then I have told you that Frank-Cordon principle, how the why the electronic transitions are vertical, and I have told you briefly about the this is not an electron density, we will call it as a uh, mole probable density. Okay, so the most probable density for a vibrational transition is always at the end of a, if you see a vibrational transition. Okay, for a simple pendulum we plot this energy. Okay, what we'll see is that, okay, so for example this is energy. Okay, and this is the x, this is plus x, this is minus x, and this is 0. Okay, so you will see that this this is how the potential energy and the kinetic energy increases. The kinetic energy is maximum when the x is equivalent to 0. Okay, and the potential energy is maximum at the extreme ends. Okay, this is like sort of a classical oscillator. Okay, so if we see in the quantum oscillator, we will see maximum probability towards, if we go on higher vibrational numbers at the ends. That is actually true in case of classicals also. While it spends a classical oscillator spends the maximum time at the two extreme ends, because there the kinetic energy is is the least. Okay, so this is vibrational. Then I have told you about diatomic molecule, what are its rotational states, what is the rotational transition, and what is the degeneracy. Then we have taken that to the three-dimensional rotation, and we'll see how the different states are coming. Okay, so this is, and then I have told you about what peaks or what type of peaks we are getting in a rotational spectroscopy. Okay, equidistant peaks by 2p, and from the 2p we can calculate the effective mass, or we can calculate the bond length. Okay, then I have introduced centrifugal distortion in the rotation, and then I have told you how the centrifugal distortion affects the rotational levels. Then we have vibrational spectroscopy, and I have taken an oscillator, and I have told you that what is a 0 point energy and what is the quantized energy level of an diatomic oscillator, for example a harmonic oscillator. Also there is also an harmonicity that occurs at when v is greater, when v is higher. So what happens is that when we increase the vibration more and more, the f of x is no longer f is no longer directly proportional to that of an x. Okay, so that is called as an harmonicity. Okay, when our amplitude of our vibration is very very high, then what happens is that f is not directly proportional to x. That time we introduce an harmonicity terms into it. Okay, so that's called as an enharmonic oscillator, that I will explain probably in the next lecture. Then we have reduced mass, and then we have how the vibrational peaks are coming and what is the transition. Okay, then we have rotational vibrational spectroscopy, where I have told you how the p, q and r branches arise and what is the difference. Okay, then I have also told you in Raman spectroscopy there are O branch and S branch. Okay, then we have taken up the question regarding the stratosphere, how the ozone is protecting the year. Then we have assignment questions where I have shown you that when the reaction coordinate is higher, the reaction, then that reaction will proceed in our will propagate more in our system. Okay, and we will get product from that of the reaction, from that reaction which has higher reaction constant. Then we have same question where we were told to calculate the energy corresponding to V is equal to 4, and then we have a similar question where we had to calculate the energy corresponding 0 point energy, so that we have calculated. So so we have finished the spectroscopy from today. From the next lecture we can take other systems, like other questions this as well, and we'll see like so this is almost a full spectroscopy that we have completed today. Okay, so yeah, meanwhile okay, this is yeah, so you have to always remember that yeah, so we always we told that how vibrational frequency is proportional, if vibrational frequency is proportional to the force constant and the reduced mass. So if we take different atoms or different atomic molecules HF, Cl, HBr, as from HF, HCl, HBr and HI down the group, the reduced mass increases. Because of increase in the reduced mass, the frequency decreases. Okay, resonant frequency decreases. So from that we can determine the yeah. Also if we take from different group, like from a single bond, for example HF and CO has a double bond. Now double bond has a more force constant, it is stronger as compared to that of a single bond. Thus since force constant is directly proportional to vibrational frequency, the vibrational frequency will be higher here. Okay, as compared to that of the HI. So single bond has lesser vibrational frequency, double bond has more vibrational frequency, and the triple bond has even more vibrational frequency. Okay, so this is evident from that is actually shown here. And also there is an effect of the reduced mass. So if our reduced mass is higher, then what will happen is your vibration frequency will be lower, and if your vibration mass is lower, your vibration frequency is higher. That is the reason if we take H axis, like hydrogen halides, if we go down the group, okay, from fluorine to chlorine, the frequency decreases because the force constant also decreases and mu also decreases. Okay, so this force constant can tell us about this vibration frequency, can tell us about the strength of a bond, or as well as we from this we'll see that HF is the strongest bond, like 970, then HCl is strong bond, then HBr is strong bond, then HI is strong bond. Okay, then we have carbon monoxide, it has a frequency of 6.48, and the force constant is 1860, so it's a stronger bond as compared to that of an anode. Okay, so with this we'll finish today's lecture. Okay, I will see you in the next one. Thank you so much.